Okay, we're still in Module 3, Methods of Proof. We're talking about direct proofs, and this is the second video. In this video, we're going to talk about definitions, because we're going to be doing proofs, and we're going to be introducing proofs by doing some very simple proofs over some simple math, because you can't learn by jumping straight into the hard stuff, right? We need to start with something relatively simple that we can work at to develop our proof skills. And to do that, we're going to be doing a lot of proofs about even and odd numbers, prime and composite numbers, and divisibility. So what that means is we need to have very clear definitions that we can use in our proofs, because without a clear definition, the proof can't be clear. Right? We need to know exactly what these mean and formally what they mean, not an intuition. I like this joke with the chicken, you know what's odd? Every other number, ha ha ha. Well, that's true, but that's not going to be a formal enough definition to help us with our proofs. So in this video, we're going to sit down and we're going to define these subjects very carefully and make sure that we have formal definitions that we can use in the future. So we're going to start with some assumptions. First of all, and it may seem kind of silly to say, but we're going to assume that the laws of algebra are correct. What that means is that if you say, for example, that x plus 1 squared is equal to x plus 1 equals x squared plus 2x plus 1, you don't need to justify that. Remember how I said earlier that in a proof is a story where every step you have to justify? Well, we're going to assume that things like this, simple algebra, don't need to be justified, that they are understood by all, that they are correct, that we don't need to explain it. The other big assumption we're going to be doing is that integers are closed under addition, multiplication, and subtraction. What does that mean? Well, so for example, for addition, I'm going to say that if I have two integers and I add them, my answer is going to be an integer. So if A and B are integers, then C is an integer. Right? So adding any two integers always gives us an integer. Similarly, subtracting any two integers will always give us an integer. Right? So here implies D is an integer. And finally, multiplication. If I multiply two integers, I'm also going to always get an integer. And what's really interesting is it turns out that this very simple concept is going to be the crux of a lot of our proofs. And so it's actually very important, and it's going to be necessary to take notice of that in our proofs so that they follow correctly. Notice that integers are not closed under division. And the reason is if A and B are integers, if I divide them, there's no guarantee that my result is going to be an integer, right? What if, for example, 1 and 2 are both integers, but 1/2 is not an integer? So integers are not closed under division. Real numbers are, however. If you divide any two real numbers, 1.0 divided by 2.0 will still be 0.5, which is a real number, not an integer. Okay, even and odd. What does it mean for a number to be even? This is something that we learned about so long ago, it seems obvious, right? Well, 2 is even, and 4, and 6, and 8, and so on. It's like every other number. But while that definition makes sense to us because we've been using it for so long, it is not a formal definition. So a formal definition says a number is defined as even if and only if it is twice some integer. So how would we write that formally? Well, we could say n is even if and only if there exists some integer, let's call it k, such that n equals 2k. So think about that for a moment. For 2, if n is equal to 2, well, 2 is equal to 2 times 1, and that 1 is an integer, so 2 is even. If n is equal to 4, which we know sort of inherently is even, what does that equal? It's equal to 2 times 2, so that's going to work. N equals 12 is even. What is that? It's 2 times 6. So see how our intuitive definition of even matches with our formal definition of even. This is our formal definition of even. Also notice that this k is just a variable. It is a placeholder. It's like using x in algebra. All it means is that some integer, which we happen to name k for convenience purposes, exists so that we can fill in our equation here. Okay, so this is the definition of even and odd. Let's see some examples. Oh, first, excuse me, we did definition of even. Let's do definition of odd. Odd numbers. What's an odd number? Well, 3 is an odd number, 5 is an odd number, 7 is an odd number. If we look back at the even numbers we did before, 2, 4, 6, 8, notice that the odd numbers come immediately after them. So we had a 2, now here's a 3. We had a 4, now here's a 5. We had a 6, now here's a 7. We had an 8, now here's a 9. So we can do a formal definition if to say that a number is odd if and only if there exists some integer. I'm going to call it k again. That's just sort of traditional, but it doesn't have to be k. There exists an integer k such that, well, see, we're saying that this is twice some integer plus 1, such that n equals 2 times k plus 1. So if you think about it, another way of defining odd would be to say it is equal to any integer, or excuse me, any even integer plus 1. That's really what we're saying here. And again, this k can be any value. That's just a placeholder. So any integer you want, we could pick an integer 100 and plug 100 in. So we'd have 2 times 100 plus 1 gives us 201. That's going to be an odd integer because we could break it down this way. So let's see some examples of this. These are the two formal definitions we're going to be using. We're going to be using this definition to say that n is even, and this definition to say that n is odd. So if I ever ask you to prove something, prove that some value is even or odd, these are the definitions you need to use. You don't want to use your intuitive understanding of even and odd because while it's intuitive, it's not formal. And that means that there could be holes picked in it. Well, you say that 11 is odd. What if I disagree? You know, why is it odd? Tell me. Well, this is why it's odd. This definition. Okay, so let's look at some examples. Is zero even or odd? Well, 0, what does 0 equal? Can we multiply it by some integer? Like 2. Right? We can indeed. So we say that 0 is even because there exists an integer k such that 0 equals 2 times k. In this example, k is 0. So even though it might seem a little odd, this is even. Let's see, could we plug it into our odd definition? Could it be 2 times anything plus 1? Well, 2 times 0 plus 1 is 3. Is 1. Can't think today. Because the 2 and the 0, 2 times 0 is 0 plus 1. What about 2 times negative 1 plus 1? Well, this is negative 2 plus 1. This gives us negative 1. What about 2 times positive 1 plus 1? Well, that's 3. So if you plug in any integer you plug in here, isn't going to work. We're never going to get 0 out. The only way we can get 0 out is if it's even, and thus just 0 times 2 times 0. Let's try another one. If a and b are integers, is 6a squared times b even or odd? Well, let's think about this. And I can say 6a squared b. Can I pull a 2 out? Yes, I can. This is 2 times 3a squared b. Well, we know the definition of even says it's 2 times some integer. How do I know that that's an integer? Well, it's an integer due to integer closure. Right? Because we're doing multiplication of integers. We know that a and b are both integers. And integers are closed under multiplication, which means a times b, and even times a, and even times 3 is an integer. So we know this is an integer, which means our original value is even because it can be written as 2 times some integer. Okay, let's do one more. Odd. Excuse me, I totally gave that away. If a and b are integers, is 10a plus 8b plus 1 even or odd? Well, remember the definition of odd was that n is odd if and only if there exists some integer k such that n equals 2k plus 1. Well, can I pull a 2k out of, or a 2 out of some of this? Yes, I can. I can factor this first part and say this is 2 times 5a plus 4b with a 1 left over. Now, again, this is an integer, right? This is an integer due to closure. Because now we know a and b are integers. We're adding and multiplying them together, so we know our result is an integer, which means we fit the pattern. This is an odd number, and it doesn't matter. Notice it doesn't matter what a and b are. They can be any integers. These are placeholders. They can be any integers, and when we substitute any integers in for them and we fill out this formula, we're going to get an odd number. Let's talk about prime and composite. What does it mean for a number to be prime? Well, a number is prime if and only if for all, remember number n is prime if and only if it's greater than 1, and if it equals some factors here, then one of these factors has to be n. It's a little more difficult of a definition, but the idea is that a number like 8 is made up of multiple factors, right? This is equal to 2 times 4, or it equals 1 times 8. Prime numbers are only equal to 1 times themselves. So 7 is a prime number, and it's only equal to 1 times 7. There's no other factors. So since there's no other factors, we call it prime. Well, this one we're going to call composite, because there's multiple sets of factors. Okay, so this is a formal way of saying that. So we're saying that if we can break it up into if we can factor it, then those factors have to be, one of the factors has to be the number themselves. The other one's going to be 1. To put this formally, we're going to say n is prime if and only if for all r and s in the positive integers, because prime numbers have to be greater than 1, and n is a prime number, or excuse me, is an integer greater than 1, that if n equals r times s, then either r equals n and s equals 1, or r equals 1 and s equals n. All right. So if n is prime, that means its only factors are 1 in itself. And this is a formal way of writing that. It's a little cumbersome, but again, we need a very formal, clear way of writing to make sure nobody can poke holes in our argument. So that's a prime number. As implied before, a composite is one where there are multiple factors. So here's another composite number. 12 is composite because it's equal to 2 and 6, or it's equal to 3 and 4, or it's equal to 1 and 12. So we have multiple choices here, meaning this is a composite number. How do we write this formally? Well, we say that n is composite if and only if, again, this is kind of an unwieldy definition, there exists integers r and s, positive integers r and s, such that n equals r times s, and now this is a way of saying there's numbers other than just 1 and the factor itself, or the number itself. We're going to say r has to be between 1 and n, and s has to be between 1 and n. Because if we didn't say that, then 1 and n itself could be the factors. Well, so how do we distinguish that there's additional factors? Well, we say there exists numbers that are between 1 and n, such that when multiplied together, we get n. Let's look at some examples. Is 15 prime or composite? 15 is composite. Why? Because 15 is equal to 3 times 5 is one pair. It also is equal to 1 times 15. But the fact that it's equal to 3 times 5 and 3 is greater than 1 and less than 15, and so is 5. And 3 and 5 are both integers, so we know that 15 is composite, using the formal definition. How about -7? Is it prime or composite? Actually, it turns out it's neither. If you recall, looking back to our definition of prime, a prime number has to be greater than 1. It's a requirement. It's part of the definition. Similarly, a composite number has to be greater than 1. So all prime and composite numbers have to be greater than 1. So 7 is less than 1, so it's neither. Now, if it were +7, +7 would be prime because the only factors would be 1 and 7. Okay, and this last one. If a is any integer, is 6a prime or composite? Well, I'm going to say it's composite because 6a has at least the following factors. We could multiply 6 and a. We could multiply 2 and 3a. We could multiply 3 and 2a. And then, of course, there's always 1 and 6a. But because we have multiple different factor pairs, this is going to be a composite number. Okay. Finally, let's talk about divisibility. What does it mean for some number a to be divisible by another number b? Well, we say that 6 is divisible by 3. Why? Well, because 6 divided by 3 is 2. Well, and 2 is an integer. Think about another way of writing this. Another way of writing this is how we usually think of divisibility, or certainly how I usually think of it, but I can rewrite this as 6 equals 3 times 2. All right. So that's multiplying both sides by 3. So we have the number, we call this a, so 6 is a, and 3 is b, and it's multiplied by some integer. Let's call that k. All right. So writing this formally, we say an integer a is divisible by an integer b if and only if there's some integer k, such that a equals b times k. So to write this formally, we're going to say a is an integer, is divisible by integer b if and only if there exists an integer k such that a equals b times k. Right. Another way to say this would be that a divided by b is an integer. So this is just an equivalent way of saying that. And to be consistent, this is the way we're going to use it in this class. So I don't want you to stop here because that's not our official definition, right? We always want to use our formal definitions, not maybe our intuition on the subject. And finally, let's do some examples here. Is 15 divisible by 5? Yes, because by our definition, 15 equals 5 times 3, where 3 is an integer. Is 3 divisible by 15? No, right? Because if we say 3 equal to 15 times k, we could work out what k is, but k wouldn't be an integer. So we can say that this does not have an integer solution. Right? So again, we're using the definition. Another way of feeling this intuitively would be to say that 3 divided by 15 is not an integer. Right? And that's really what we're saying with our definition here. And finally, if a is any integer, let's cross it out, there's a typo. If a is any integer, what numbers is 6a divisible by? Well, we sort of saw some of these before. We could do 6a is divisible by 6 and a. It's divisible by 2 and 3a. It's divisible by 3 and 2a. And it's also divisible by 1 and 6a. So what that means is any of these, we could say 6a is divisible by 3. All right, looking at this one right here, because 6a equals 3 times what? Well, 2a. And we know a is an integer, so this is an integer under integer closure. So these definitions, I know this video took a while, but these definitions we're going to use over and over and over and over again. So I want you to be very comfortable with these definitions for even and odd numbers, prime and composite numbers, and what does it mean for a number to be divisible by another number.